Hi guys, in the last video we talked about the definition of bivariate extreme value and the limiting distribution of the scaled version of the bivariate extreme value. So basically the result that summarizes what we talked about in the last video is as follows. Suppose you have data from a bivariate data IID with joint CD of F. This is the definition of a bivariate extreme value I gave you. Now, if there exist constants a(n), bn, cn, and dn, where a(n) and cn are positive, bn and dn can be any real number, such that the scaled version of the bivariate extreme value, this is a scaled version of the first component, the scaled version of the second component, which I showed in the last video is equal to this. And if this approaches G for a non-degenerate CDFG, then the possible forms for G can be uncountably infinite. So this is very unlike the univariate case. Remember, in the univariate case, if the limit exists, it must be of one of three types: the Gumbel type, the Fresher type, or the Weibel type. But unfortunately, that does not hold in the bivariate or multivariate cases, right? Now, if the limit G exists, it's known as, let me write this down. If G exists, it is known as right, and for short, this is B, E, B, D, all right? So if the limit exists, then it's known as the bivariate extreme value distribution, or BEVD. Now, in this video, what I'm going to do is that, given that the limit exists, I'm going to show you a procedure to determine the form of G, in other words, the form of the bivariate extreme value distribution. That's the purpose of this video, right? So let me start by explaining the procedure. So the heading for this video is follows: how to determine G if it exists. Okay, so that's the heading for this video. So the procedure is as follows. The procedure has the first step is to find right. So the first step is to find the marginal CDFs Fx and Fy of F. Remember, F is a bivariate CDF. So Fx and Fy are the univariate marginal CDFs. Step 2. Because these two are univariate distribution functions, they must, they must satisfy the extremal types theorem, the univariate extremal types theorem, which says that that fx and fy must belong to one of the three types, the Gumpel, Frechet, or Weibull, right? So that's what step 2 says. Now, step 3, if suppose fx and fy belong to the Gumpel limit, right? It must be one of the three, right? Suppose they belong to the Gumpel limit, right? Then take, maybe I should put an A here, okay? Take the constants A and B and C and D and as follows. Excuse me. A as this, your Bn as this, and your Cn as this, and your Dn as this, okay? Now, gamma x and gamma y are the functions that must satisfy condition 1 of the extremal types theorem. Remember, you should remember condition 1 of ETT, it involves a function gamma. So this is the gamma x here is the function for the marginal CDF of x, and this is the function for the marginal CDF of y. Okay? Now B, part B of part 3, if fx and fy belong to the Frechet limit, then take A and the four constants as follows. So you choose an as the inverse function of the CDF of x at 1 minus 1 over n, Bn 0, Cn the inverse function of the CDF of y at this, and Dn as 0. Okay, so this is part B of part 3 of the procedure. Now, part C, suppose, okay, if the two marginal CDFs, fx and fy, belong to the Weibull limit, right? Then take the four constants as follows. So take an as the upper end point of the marginal CDF of x minus this. All right. Take Bn as the upper endpoint of the marginal CDF of X, Cn as okay, and finally Dn as the upper endpoint of the marginal CDF of Y. All right, so this completes part 3 of the procedure. Now finally, part 4, this is the final step of the procedure. Determine G is the bivariate extreme value CDF as the following. As the limit as n approaches infinity of the following. Okay, so this is the 4-step procedure for finding the form for G. Although it is, the possible forms can be uncountably infinite, you can determine, or there is, I mean, this is a procedure to determine G if it exists, right? Now let me illustrate this 4-step procedure by an example, right? So that's what I'm going to do next, is to give you an example illustrating this procedure. So it's example 1. Suppose that the joint CDF of X and Y is given by this. Okay. The question is to find the bivariate extreme values CDF G if it exists. So I'm going to follow the procedure which I just described. So the first part of the procedure is to determine the marginal CDFs of X and Y. All right, so you may recall, to find the marginal CDF of X, you put Y equal to infinity into this, right? So you get, if you put Y equal to infinity over here, you will get the following. Right? So that's the marginal CDF of X. And similarly, the marginal CDF of Y, you put X equal to infinity, right, into this formula. And if you do that, you'll get okay. So step 1 completed. Now step 2. For step 2, we need to figure out which of the 3 limits that the marginal CDFs belong to, whether it is Gampel or Frechet or Weibull. Now, we have done enough examples on that, on the ETT, I mean the univariate ETT before. So you shouldn't have much trouble doing step 2. All right, now before we can find the limit, right, we need to determine the upper end points. All right, so I'm going to set the CDF of X equal to 1 and solve for X in order to determine the upper end point, right? All right, so this implies that this is equal to 1, right? And this implies that 1 plus is equal to 1. This implies that e of minus x is 0. So taking the logs, you have minus x equal to minus infinity. So x is equal to plus infinity. Hence, the upper end point of the marginal CDF of x is equal to plus infinity. Now let's check condition 1. Okay, I hope you remember condition 1. We did that while ago. Okay, so condition 1 is that you need to find the limit of this, right, as t approaches the upper end point, which is infinity here, right? And if the limit of this is equal to e of minus x, then we can say that the marginal CDF of x belongs to the Gumbel limit. All right. So let's see what happens. All right. Okay, guys. So here we go. So this becomes equal to the limit as t goes to infinity of 1 minus 1 plus e minus t minus x gamma. Okay. Okay. All right, guys. Okay. Now let me take this away. All right. Now, the question is how to simplify. I mean, we can simplify this as follows. So we can write this as limit as t goes to infinity. 1 minus of this, right, can be written like right, and similarly the denominator can be written like right. Now as t goes to infinity, this guy goes to 0, right, and so is this one. Because the gamma function is positive, this must also goes to 0, right? So you have 1 plus 0, 1, 1 plus 0, 1. So this is the same as the limit as t goes to infinity of okay. And these two terms cancel, so what you get is the limit as t goes to infinity okay, and this is equal to e of minus x if we choose gamma x of t to be identically equal to 1 for all t, right? Hence condition 1 holds, right, and fx belongs to the Gumbel limit. Okay. right? Okay, similarly, I'm not going to repeat the calculations. I'm sure, I mean, given the number of examples we've done on the univariate ETT, I'm sure you can do it. Similarly, it can be shown that the marginal CDF of y also belongs to the Gumpel limit. Right, with the same expression for gamma y will again be identically equal to 1 for all t. All right, so we finished part 2 of the procedure, of the 4-step procedure. Now we can go to part 3 of the 4-step procedure. Now, the part 3, you may recall, is to find the constants an, bn, cn, and dn. Right? Now, because both marginals belong to the Gumpel limit, right, we choose an as follows. This is, you may recall, this is the formula I gave you for an. Now, because gamma x is identically equal to 1, this must be equal to 1, right? Now, in order to find Bn, we need to find the inverse function of the CDF of x at 1 minus 1 over n. So what we need to do is we need to set the marginal CDF of x equal to this, and then solve for x in terms of the rest, right? So that's what I'm going to do. Right, and this implies that minus x equal to minus log, all right, and this implies that x is equal to log of n minus 1, right, and hence the inverse function of the CDF of x at this is equal to log of n minus 1. So n is equal to 1, and the bn is equal to this, which is equal to log of n minus 1. All right. Similarly, I'm not going to repeat the same calculations again, but similarly, we can show that Cn is equal to 1 and dn is equal to log of n minus 1. Okay. Right. Okay, so we're done with step number 3 of the 4-step procedure. Now, the final step, step number 4, I'm going to start with that now, right? Here we, so this is step 4 of the procedure. The step 4 says that G, if it exists, right, is equal to the limit as n approaches infinity of the following. Okay. All right. So okay. So let's see how we can find this. This is where your calculus comes in handy. I'm sure all of you know calculus better than I do. All right. Now, if you put, we know that AN, we know BN, CN, and DN. So if you put, well, before I do that, we also know capital F, right? So remember the form of capital F that was given in the question, in the example. This is the formula I gave you in the example. Right, to the power minus n. Okay. Now, in the next step, I'm going to substitute the formulas for AN, BN, CN, and DN. Right. So this is going to be the limit as n approaches infinity of okay. And in the next step, I'm going to simplify some of these terms. Now, e of minus log of n minus 1, I'm sure all of you know, is equal to 1 divided by n minus 1. So the terms can be simplified as follows. All right, this term here simplifies to this, and this one simplifies to this, and this term here simplifies to this. All right. Okay, guys. Now, in the next step, I'm going to do a rearrangement. Okay, you'll see what I'm doing in a sec. So I'm going to write this term as follows. Okay. You'll see in a minute why I'm doing this, okay? And this one, similarly, I'm going to write as follows. And this one I'm going to write as okay. All right, guys. Okay. Now you see that you see what I'm going to do in a sec. I'm going to, the reason I have introduced the 1 over n is for the following. I'm going to pull out all the 1 over n's outside, right? And in bracket, you're going to have the following here. You see what I'm doing. close bracket, and close bracket to the power minus n. Okay. All right. Now in the next step, I'm gonna let me call what is inside the inner brackets. Let me call whatever inside here, just for easiness of writing. Let me call that z or z, right? Okay. Now, in the next step, I'm gonna write this as limit as n goes to infinity of 1 plus z to the power n minus n. You see what I've done? Let me show you both at the same time so that you can see what I've done. So this thing here inside the inner brackets, I call it z. So what you have is 1 plus z divided by n power minus n. Okay? Right. Now this you can write like this: the limit as n goes to infinity of okay. Yeah, and this you may recall from, I did several examples where I used this fact that this is equal to the limit of e of z to the power minus 1 as n goes to infinity. So I'm using the fact that the limit of this is equal to e of z, right? Okay. Now, this is the limit as n goes to infinity of e of minus z. Now I'm gonna put back substitute back the formula for z, right? Which was the following, right? The formula for z was this. Okay, this you may recall, right? This was the formula for z, right? Now, as n goes to infinity, you will see that n divided by n minus 1 goes to 1, and this goes to 1, and this goes to 0, right? So the last term disappears, and the first term becomes e to the power minus x, and the second term is e to the power minus y. So what you have, so the limit that you have is the following: e of minus e okay. So hence we have shown, I know it's been a long procedure, but if you do a few examples like this, you will know the feeling. Hence, we have shown that the bivariate extreme value distribution function g of x comma y is equal to e right. So this completes the example, right, and also completes this video. In the next video, I will talk about representations for the bivariate extreme value distributions. As I said, although the possible forms are uncountably infinite, the forms can be unified into certain representations, and I will talk about them in the next video.